Hello, my name is Tim Woodbury. I'm a senior aerospace engineer with Emergent Space Technologies. Today I'm going to talk to you about DASHER. DASHER is our autonomy software for distributed space missions.
Before we get started, I wanted to thank several contributors to this work. DASHER was originally funded as a small business technology transfer contract with NASA Goddard. I want to particularly acknowledge Anthony Gillette and Rachel Misbin, students at the University of Pittsburgh, who did a lot of the implementation of the second of the two demos I'll show later on. The rest of this talk will briefly cover our motivation for developing this autonomy software. I'll talk about its design and core functionality, and then move on to speak to its specific implementation as a CFS application. I have two demos to present. The first is a Cislunar injection mission. The second is a cooperative Earth observation mission. Those will be the main focus of the presentation, and then we'll wrap up. Recently, we've seen commercial and government interest in cooperating fleets of small satellites. A number of commercial companies are deploying LEO constellations. We've also seen announced government missions that will require cooperating spacecraft to operate in the Cislunar environment, such as LunaNet. Existing LEO clusters function with minimal onboard autonomy. Most actions are commanded from the ground. We believe that as operations get more and more remote, it's going to be more and more important to have onboard processing that can handle routine operations, driven mainly by transmission lag and expense. The sorts of functions we're thinking about would include fault detection and recovery, power management, maneuver planning, things of this nature. DASHER is a suite of applications for event-driven execution of a plan. We use a hierarchical execution model in which we have a centralized executor that monitors distributed executors that run on every single individual platform. The core executors act on plans that are finite state machines with transitions between states triggered by telemetry. Plans are provided either from a user or from some other app. If you look to the right on our sort of notional mission implementation, you can see we have a common set of applications that run on every platform. And then we have this coordinator vehicle that has this additional mission coordination software. The DASHER software is organized into three core applications. These are the Mission Manager, Execution Manager, and Timeline Manager. The Mission Manager's primary function is to coordinate and oversee the overall mission. It's also the primary point of contact for any commands coming from a ground system. Execution Manager and Timeline Manager together are the core autonomy stack that runs on each vehicle. Execution Manager carries out the platform's plan with the associated event-driven state transitions. Timeline Manager is a specialized application for queuing and deconflicting tasks with competing resource needs. Our vision is that one Mission Manager instance will be active at a time and will manage a fleet of DASHER-enabled vehicles based on feedback received from the execution managers on every vehicle. Timeline Manager running on each vehicle is going to send and receive commands coming from specialized applications for controlling sensors, performing maneuvers, and other related functions. Both Execution Manager and Mission Manager have a common core software structure for managing a plan and receiving telemetry. Each executor follows a plan. A plan is simply a binary file that's loaded at startup. The main loop consists of two functions for receiving telemetry and checking to see if a state transition has occurred. When telemetry is received, it's processed by a telemetry processor object. The telemetry processor object is customized for each mission, and it buffers messages that satisfy some particular criteria of interest. For example, you might buffer messages that indicate the spacecraft has entered into a particular set of navigation coordinates. The check state function then accesses the buffer during its call, and if it finds that an event has been buffered, it executes an associated state transition by sending any commands that need to be sent to the software bus. Commands can be associated with an event, or can be associated with either entry or exit from a state, depending on the mission. This is the core executor loop used in both the Mission Manager and the Execution Manager DASHER applications. Let's talk about the Timeline Manager app. The timeline manager is responsible for implementing a timeline of tasks that need to be executed by the system. It manages between different tasks based on the resource needed by the task, the relative priority of a task, and then its execution state. Tasks can be in several states from when they're scheduled to when they're completed. Timeline Manager cares about two types of external apps. We have planners, which are things like Execution Manager, which generate tasks that need to be executed by the system. And then workers are some class of applications that receive tasks from Timeline Manager, actually perform the task by sending commands to a software bus, and then generate a response that's received by Timeline Manager. If we look at this figure at the top right, you can kind of see notionally how this works. We have some task coming from the spacecraft message bus from some planning application. That task specifies the resource, priority, and time window associated with the task. Assuming that the task is added by Timeline Manager, which mostly requires it to be a valid message, Timeline Manager schedules the task, and once its time window is entered, Timeline Manager sends out a task response, which is going to tell an external worker app what is the associated time window of the task and what is its ID. That worker, assuming it receives the app, performs the task, and then sends back a task update indicating that the task has been scheduled and then that it's been completed. That's received by Timeline Manager, which will then remove the task from the queue, freeing up resources for any other tasks that might need the same resource. This figure at the bottom right indicates how Timeline Manager deconflicts between different tasks that require the same resources. So we have three tasks here. Task A and Task B both need resource 1. Task C needs resource 2. Task A, because it's got the highest priority and begins first, is going to be the first task that Timeline Manager will send out a task response for. And until it receives an update indicating that task has been scheduled or completed, Timeline Manager is going to continue to reserve resource 1 for Task A because it has the highest priority. Meanwhile, Task C will begin immediately at Task 2. We'll send out a request then because it does not use the same resource and there's no conflict there. So Task B may be skipped entirely if Task A isn't completed before the time window of Task B closes. It just depends on the system and how it handles these different tasks. That's all I want to say about Timeline Manager. I'd like to move on now and talk about the actual plans used by DASHER just a little bit. I've talked about the plans quite a bit already. The main thing to be aware is that a plan represents a finite state machine with transitions between states being driven by events. Events in this case refer to the reception of telemetry that satisfies some pre-specified conditions of interest. And that could mean many different things. We've already gone over some examples. The important thing to be aware is that any event and any state transition into a state or out of a state can have an associated command, where a command is some message that should be put onto the software bus where it can be received by other applications. If you look at this figure on the right, you'll see kind of the simplest type of plan showing both. We have two states here. Each state has an entry command and an exit command. We have transitions possible from state 1 to state 2, then back from 2 to 1, and then from 2 to itself. Each of those transitions potentially has an individual event associated with it, and that event may have a command associated with it. This gives you a lot of flexibility to specify different types of missions, with commands being associated with events, states, or with neither. So that's all I have to say for now about core software functionality. I'd like to move on now to talk about how we've implemented the apps originally as CFS apps, and then what we're currently working on as part of ongoing development. For the STTR, the DASHER applications were written in NASA's core flight system. We used a three-layer structure to try to isolate the core functionality away from CFS-specific code. To do that, we have these application, adapter, and service layers for every app. The application layer is the direct interface with the CFS message system. It's responsible primarily for setting up publishers and subscribers and receiving and sending messages. The adapter layer is the interface between the application and the service layer. The service layer contains the core functionality for each app, such as the state machine logic or the task queuing functionality that's a part of Timeline Manager. Currently, we're in the process of converting DASHER to use Emergent's Gear architecture. Gear is the topic of another talk in this workshop, so I'll only cover it briefly. There are different middlewares, such as CFS and ROS. They all have different APIs, and they're all used different platforms, different missions. Typically, the middleware is not up to us as the software provider. Gear is an abstraction for any particular middleware. So rather than writing a CFS app and then having to port it to ROS if you need ROS, your developer will just write a Gear app, and then Gear will provide an interface for both ROS and CFS. If you need to use a new middleware, then you just write a Gear interface for that middleware, and you already have access to our complete set of software that uses Gear. So that's the end of our discussion of the implementation of DASHER in CFS and then now within Gear. I want to move on now to talk about the first of the two examples I'll present, the Cislunar mission demo. In this mission, we have a single spacecraft using the DASHER software approaching the moon on a parabolic polar orbit. That spacecraft is going to autonomously execute a maneuver that will circularize its orbit and then begin some generic lunar science mission, which at this point is notional and is outside our scope. In this demo, we have our DASHER flight software running within a Docker container, sending messages that are received by Emergent's Ascent simulation. Ascent provides us both with dynamic simulation as well as visualization capabilities that we'll see in a few slides. We have two helper applications that we've written to bridge between the Ascent simulation and the DASHER software. These act as interfaces to a spacecraft message bus. And our DASHER plan in this case is going to be pre-programmed with a set of coordinates and an associated maneuver that should actually be sent out and received by the Ascent simulation that will cause the spacecraft to enter this circular polar orbit that represents its target for this mission. The design for this mission is quite simple. Mission Manager is going to monitor navigation telemetry. If it detects that the vehicle has reached the target circular orbit, it's going to send a command to Execution Manager. That command will cause Execution Manager to enter some generic operating state that's associated with the polar orbit. Execution Manager monitors the same navigation telemetry, and if it detects that the vehicle has reached a target set of coordinates, it sends a command that's going to cause the vehicle to perform a delta V that circularizes the orbit. Timeline Manager is responsible for interfacing between Execution Manager and the Ascent simulation. Timeline Manager receives a task from Execution Manager and actually forwards a maneuver to the Ascent simulation, which has no direct a priori knowledge of the type of maneuver or its magnitude. Here's the visualization of the Cislunar mission. To the left and right, we have the state trees for Execution Manager and Mission Manager. The active state is highlighted, and you'll see them transition as the mission evolves. Initially, we're on this parabolic polar trajectory. Once the Execution Manager detects that the mission has reached a set of coordinates, it transitions to this operating maneuver state, sends a message to Timeline Manager. Timeline Manager queues a task, sends a maneuver to the Ascent simulation. The Ascent simulation executes that maneuver, circularizes the orbit. This causes a transition in the Mission Manager. Mission Manager sends out a message, which is received by Execution Manager, causes it to advance to this terminal operating polar orbit state. And this represents the end of this Cislunar mission. I'd like to move on and talk about the distributed Earth observing mission. This is an example that was put together, as I mentioned, by the students at the University of Pittsburgh. What we're looking at in this scenario, we have a cluster of 4 Earth-observing satellites, and they have a series of 10 arbitrarily chosen targets that they need to image. In this mission, the mission manager is configured to assign particular targets to particular spacecraft online during the mission based on a simple proximity, who's closest. To account for failures, there's a protocol where if there's no response from the spacecraft that's assigned to a target, mission manager will move on to the second and then the third closest spacecraft until it gets a successful response indicating the image has been taken. The simulation is conducted in the 42 simulation environment. We have shown here an image visualizing the output from the 42 simulation. And then we're actually going to run DASHER in this mission on a set of ARM pink boards, which are flight-like processors that are capable of running the DASHER apps. We'll have the 42 simulation running on a laptop, communicating with these 4 pink boards over network and passing messages back and forth between them. The mission design in this case is more complex. However, we're using the same software on each vehicle, so it is relatively simple. A lot of this mission relies on a helper app that interfaces between mission manager and sort of the external knowledge of the system. The helper app has the coordinates of the targets. It also keeps track of the navigation data and is responsible for recognizing which vehicle is closest to a target at a given time so that it can interpret the commands from mission manager appropriately. The helper app notifies mission manager when a target is in range of the cluster. The mission manager sends out responses indicating, okay, the first closest spacecraft should target the currently visible target. And then if it fails to get a response, it'll elevate that to the second closest spacecraft and so on. The execution manager design is pretty simple. Execution manager, if it's online, receives a message from mission manager, sends out a message that goes to timeline manager. Timeline manager forwards that message to the 42 simulation, and everything will work successfully from there. To simulate failures, we're actually just going to kill the applications on some of the boards during the mission as it runs. In this current mission, we have a dropout of spacecraft 2 about 30% of the way through the mission, and then a subsequent dropout of spacecraft 3 about 60% of the way through the mission. We have this timeline here at the bottom right indicating the target ID and the spacecraft that will capture images of each target. You'll see we have some of these list 2 spacecraft IDs for a spacecraft that is initially assigned and then is killed before it can successfully complete the mission, causes mission manager to task another spacecraft to take an image of that target. So let's move on and look at the 42 simulation video. Now, this video has a lot going on in it. I'm going to go through it pretty quickly. We have these 4 consoles on the left corresponding to the raw console output from each of the 4 pink boards. The corresponding spacecraft are shown on the right. Note that their positions in the quadrant of terminals are different than their positions in the visualization. In the top left, you'll see a sequence of yellow text passing by. That happens each time Mission Manager detects a target's in range and sends out a command. Corresponding yellow text will then appear on one of the consoles for the spacecraft, indicating that it's received the message. Once that happens, you'll see a very quick transition over here on the right. We're not doing any kind of slew dynamics, so each spacecraft instantaneously slews to face the target, and then back to its original orientation. Now, we've just had spacecraft 2 drop out. You can see that it's been killed here at the bottom left. And spacecraft 3 is being assigned to image this target. Once that's complete, spacecraft 3 will be the closest spacecraft to the next several targets in succession. And you'll see it make a series of instantaneous slews each time. We skip the time in between observations because nothing of interest is going to happen there. So we've now completed imaging the first 6 targets. We've moved on to the 7th target. Spacecraft 3 is going to be killed off before it can take an image of this target. And that'll cause Spacecraft 1 to take an image of this target. We're going to have to wait several seconds for Mission Manager to time out and to elevate the command to the next closest spacecraft. But we can see Mission Manager is now sending out that command, and it's been received. Spacecraft 1 has executed the maneuver, and now it's moved back to its original orientation. And we move back into the flow of things, and additional time is going to pass. Spacecraft 1 is going to continue to be the closest to the next remaining 3 targets, now 2 targets, for the cluster to image. We'll go ahead and let this run all the way through. We're now imaging target 8. And finally, we're going to image target 9, and that'll be the end of this demo. That's the end of the cooperative Earth observation mission. I'd now like to summarize, and we can move on to the end. We've introduced DASHER, which is a set of flight software for autonomous execution of a plan. Originally, DASHER was implemented as a suite of CFS applications. Our current development is transitioning it into a gear-based application, which we use Emergent's gear software to develop a set of apps that can work independent of the underlying middleware, which could be CFS, ROS, etc. Finally, we've demonstrated DASHER in the loop for 2 demos, Cislunar injection mission and cooperative Earth observation mission.